Hello everyone. Today is the 45th day of Leetcode 75 challenge. Let's begin with the 45th question. Question 1466. Reorder routes to make all paths lead to the city 0. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given an integer n representing n cities numbered from 0 to n minus 1. You are also given a list of roads called connections. Okay, so we are given a list which name is connection, which contains the roads basically. Fine. Where connection of I is equals to AI, comma BI means there is one way road from city AI to city BI. Okay, basically we have given a directed graph here. Okay, where A, comma AI, comma BI means A is going towards B. These roads form a tree structure. Please keep this in mind. It's a tree structure, meaning there are exactly n minus 1 roads, and all cities are connected without forming a cycle. The capital city is city 0. Your task is to ensure that every city can reach city 0 by following the directions of the road. Fine. So they said that it is a tree structure. Why? Because we have been given n minus 1 roads exactly. And what are the roads basically? Those are the edges, nothing else. Fine. So it is clearly said that connection list which is given to us contains exactly n minus 1 edges. Fine. So it is guaranteed that all the cities are connected by these connections and they are not forming any kind of cycle. Fine. So what does this implies? This implies that a graph with n nodes, okay, and n minus 1 edges that is connected by definition is a tree. Okay. Because there are no cycles, there are no disconnected components. So it is a tree. Okay. Pretty simple. So let's take look here we have how many nodes? We have three nodes, right? How many edges do we have? We have two, which is basically n nodes and n minus one edges. So it's a tree, right? You cannot call it as a graph since the structure is of a graph, but it is not a proper graph, right? A graph could be connected or disconnected. It could have multiple disconnected components also, right? But it forms a tree, proper tree. And if connections array might had more than n minus one edges, suppose this one, this connected this way, this also connected this way, then it is a proper graph which could contain cycles and it won't be a proper tree. Fine. So that is why we could say that it is proper tree and we don't have to worry about anything. And we have to reverse, or you can reverse the direction of some roads if necessary. It is guaranteed that each city can reach city 0 after reorder. Fine. They're asking us to reorder the road so that we could reach city 0. Fine. So means there are some edges which are not allowing the particular city to reach city 0 or the capital city. So our final output should be the minimum number of edges that we need to change or reverse to make all paths lead to city 0. Fine. So basically there might be some paths which are not directed towards the city 0. Okay. So we have to make them reach city 0. So we have to change the direction, of course. So we have to basically return those edges, that how many edges did we reverse so that we could reach city capital 0. Fine. Now let's understand the constraints now. The n value could be from 2 to 5 value 10 to the power 4, and connections length, or the array length, would be will be equals to n minus 1, of course. And connections value, connection of I means a comma b, will be of 2 length every time. And a of I, ai and bi will be from 0 to n minus 1 because it is a tree. That's why, and they will never be equal, which means that there would be never 2 comma 2 because there could not be a tree that is pointing towards the same node, right? So this is all about the problem explanation. I hope you understood it. Now let's move to the next slide. Let's understand the input output of the problem. Okay. So this is the graph given to us, or you could say a tree given to us. So let's make it okay. 0 is pointing towards 1, right? 1 is pointing towards 3. Great. 2 is pointing towards 3. 4 is pointing towards 0. Fine. 4 is also pointing towards 5. Great. Now, if you could see how many nodes are there, 1, 2, 3, 4, 5, 6 nodes are there, and how many edges are there? 1, 2, 3, 4, 5 edges are there, right? So it's a tree basically. Okay, and this is the capital city. Now let's check how many cities can reach capital city, or let's check how many cannot reach capital city. Fine. So can 4 reach capital city? Yes. Can 5? No, because the road or the edge is pointing away from the capital city. Fine. So we have to reverse this towards 4. Now can it reach? Yes, it can. Could 1 reach? Never. So we have to reverse the edge again here. Okay. Could 3 reach? No, it cannot. So we will reverse the particular edge here. Fine. Now, how many edges did we reverse? We reversed nearly or equal 3 edges here. That then we are able to reach to city 0. Fine. Therefore, the output is 3 here. Now let's check for the second case example. 1 is pointing towards 0. 1 is pointing towards 2. 3 is pointing towards 2. And 3 is pointing towards 4. Fine. So how many nodes are there? 1, 2, 3, 4, 5 nodes are there. How many edges are there? It is 4. Fine. Now, could 1 reach 0? Yes. Could 2 reach 0? No. So we have to reverse the edge. Then can 1 reach 0? So it is good. Now, could 3 reach 0? Yes. You can look at the edges now. Okay. Could 4 reach 0? No, because the edge is opposite direction, right? So we have to reverse this particular edge. Now it can reach 0. So the output is 2 here, and we also reversed only 2 edges in this case, right? So that is the input output explanation. I hope you understood this. Now let's move to the next slide. Before going to the further slides, let's understand what is depth first search in graph. Okay. So DFS, which is depth first search, is a graph traversal algorithm that explores as far as possible along each branch before backtracking. So in a simple language, in if you remember in tree also there was DFS. What is the simplest and the common difference between a tree and graph is that suppose this is a binary tree, and if you connect it, it is a graph. So a tree has to be unconnected, whereas graph could be connected and unconnected both. Okay. So let me draw a graph. Okay, let this be a graph. I'm trying to draw a directed graph here. Okay, okay, and this one, then will come here. Okay, so I have just this is a random graph which I have drawn. Okay, suppose you started with one. Okay, from one, where you can go to two also, and you can go to three also. Correct. So, but you cannot go twice all simultaneously, right? Into both of the nodes. So what you will do? You will think of going to the two first. So you went to two first. Okay. Then you tried going after from two. Then you tried going more down, more depth, but you were not able to because the arrow was pointing in different direction. Since it is a directed graph. So what you did? From one to two you went. Then you came back. Then you went to three. Okay. I will write it this way. You came to three. Then you could see that from three you can go to five also, right? So you came to five. From five you cannot go to four because the direction is this way. But from five you could go to six. So you came here. After that, you saw that you cannot go anywhere else because it is the end. So you came back. That is a backtracking part. Okay. And if you could see, explores as far as possible along each branch. Okay. Basically going to the depth. So we went to the depth. Then you came back, backtracking. After that, you could see that you cannot access four or five. Right? So what you do, usually if you remember, we draw a for loop to go to each and every node. One was visited, then two was also visited, three was also visited, five was also visited, six was also visited. It was the four which was not visited. So when we go through a for loop, which basically goes from 0 to n nodes, and we mark everyone visited, right? So when you come to 4, you say it is not visited, so you keep it as 4 here. Okay. But you cannot go to 5 because it is already visited, and 2 because it is already visited. So this is what a depth first search looks like. Okay. And how it works in a theoretical manner, if you could see, we start with the source node. It could be anything. It could be 2 also, it could be 3 also, right? But I started with 1. We mark it as visited, visit one unvisited neighbor recursively or using a stack. So this is not necessary. Recursively, when we use, it already uses a stack space. Okay. That's the thing. And we mark it as visited so that we don't visit one node again and again. We backtrack when no unvisited neighbors remain. If you can see, there are two cases when you backtrack. One is that you reach the end, or one, for example, if it was a circular, suppose it was a circular graph, okay? Suppose I am marking with this yellow mark, okay, the latest mark. Suppose instead of going after 5, we are going to 4, and we are going to 2, and not this one. Let's take it as this, okay? So the path now is this way, okay? It's a circular one. So when you start with 1, when you go to 3, when you go to 5, then you go to 4, then you go to 2, then when you come to 1, you see that 1 is already visited, right? So you go back. So this is another case when you backtrack. Okay, the two cases I told you. And DFS can be implemented using recursion. Okay, and this is not necessary explicitly stacked. It was it's an uncommon practice, but I just have written here that if you want to use, you can do it. And why is it efficient? The time complexity comes out to be V plus E. V means vertices, E means edges. What are the edges? These are the edges. What are vertices? These are the vertices, which are also called as nodes. And each node and edge is visited once. Okay. Therefore, the time complexity for comes out to be V plus E. V means for each vertex, you might go to n number of edges, right? And space complexity is OV of O vertices because we store number of vertices in the array. Okay, we don't store the edges also. That is not possible. And for recursion stack or visited array. Okay, and it is efficient for graph traversals where full exploration is needed. As you can see, we needed a full exploration in this case, and solving problems that require backtracking or component discoveries. The component discoveries, I will get a question ahead, then we'll look at it. Now, where we can use this DFS? Okay, I've written some of the question examples and topics where you can use. Suppose if you get a question which is related to connected component detections, okay, like in undirected graph, DFS can be find and label all disconnected components. Disconnected components are basically, suppose this is a graph, this is another graph, this is another graph. So there are three disconnected components, but they are a single graph, but all are disconnected. Okay. So output for this particular will be 3. So in this case, we will use DFS, not BFS. It is not much helpful in that case. Or in the cycle detection, also you could use that. Suppose if the graph has a cycle or not. Okay. This is a cycle, correct? And you could find the questions in for directed graph, for undirected graph, right? And topological sort is the DAG. So when you have to check for a DAG, DAG means what? Directed acyclic graph. This stands for DAG. Fine. Directed means you have an arrow only in one direction, not both directions. Acyclic, it does not contain the cyclic. Suppose this. This does not contain a cycle, right? So this is what a DAG is. So if you have to look for a DAG, whether a graph is a DAG or in question related to the DAG, then in that case you have to study about topological sort and use that concept there. Okay. Path finding without weights, when you have to find a path in a given graph, okay, like solving maze-like problems, okay, without weights, and there could be also a path finding with weights, fine, solving puzzles like Sudoku and coins and all that stuff. Breach and articulation point detection in networks. DFS helps identify critical connections, so removal disconnects the graph. So basically, if you have to look for articulation points and you have to remove that, or the bridge you have to remove that, in that case, we use this concept, or we use the DFS in that case. We will follow up with this all these questions as per our sheet. And strongly connected components. Like for example, if you could look at Kosarazu's and Target's algorithms, both uses DFS to find SCCS is in directed graph. Strongly connected components are the components which cannot be break into multiple pieces, right? Okay. So I hope you understood the depth first search in detail. I have not gone in much more depth because it is not necessary. Because if you are studying graph, you should already know about this topic. But yeah, I have figured out some of the things of BFS which will help you in solving the problems. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Fine. Let's do it by understanding the goal again, right? So we are given n cities labeled from 0 to n minus 1 and a list of one-way routes, which is basically we are given directed edges. That's all. Okay, which is represented as in this form. We already understood this. Now, these roads form a tree structure because exactly n minus one connections are there, right? With all cities connected, and even if we reverse the cities according to the question, we will be able to reach the particular capital. And there are no cycles. There are no multiple components. Fine. So we could clearly say that it is a tree structure, and we don't have to worry about anything. Now city 0 is the capital and we want every other city to reach city 0 by following the directions of the roads. Since some roads are facing away from city 0, we may need to reverse this, some of them. Fine. Now task is to find the minimum number of roads. Please keep that in mind. We have to basically return the number of the reversed road, right? Or the reversed edges. To solve this, we can use DFS traversal starting from city 0 and count how many roads need to be traversed. So here, if you pay attention that we have to return numbers, right? And I already said we will count how many roads need to be reversed. Okay. So one way could be we could create a new tree and reverse the edges which has to be reversed and take the count by doing that. But that will be a lengthy process and another space complexity will increase and time complexity will increase for no use. But rather than that, we will try something else. Okay. And secondly, we will try using DFS because we can use DFS, but it will not be as much intuitive as DFS because since we will be going in a depth, fine, we will come from this node to this node, we will check the edge, we will come from this node to this node, we'll check the edge, and we will go back, right? But in DFS, what will happen at one go, you will try to check multiple edges in the particular level, right? Okay, it might give you the answer, DFS might give you the answer, but it is not as intuitive as the DFS part, right? So using DFS is makes much more sense in an interview rather than using a DFS here. But you are free to use DFS and complete the solution. Okay. Now let's visualize the process. How we're gonna solve this problem. Okay. So let me draw a graph here. Okay. So I've drawn a random graph structure here. So let's think of the solution. Okay. So think of cities as a node. Okay. Basically, these are the nodes, which are cities basically, and these are the edges, which are the roads. Okay. We aim to orient all paths such that there is a validly directed path from city to city 0. Okay. And we will be using DFS first of all. Okay. And rather than creating a new graph, what we will try to do is that we'll count the edges which are not pointing towards the capital city while we are doing the DFS. Okay. So basically, in one traversal, single traversal, we will try to figure out how many edges to be reversed. So what comes to your mind? What happens I if I modify this graph? Okay, I will just modify the graph. I will draw or I will modify the edges. Suppose this is the original edges, the yellow color. Now we'll add new edge in the opposite fashion. Fine. Basically, I will remodel the graph having bidirectional edges in it. Fine. Great. So I have done this. Okay. Now, could you reach the graph or the edge which you were not able to reach before? Could you reach? What I'm trying to say there. Suppose you didn't had this modified edges, right? And you came from zero, and you want to go from 0 to 1. Will you be able to go? No, right? But from 1, can you go to 0? You can go, which means that it is directed towards the capital city, so it is an acceptable solution. And 3 also directed towards capital city. Fine. But this node, fine. The edge is directed away from the capital city. Now, whenever we do a DFS traversal, we always go in a depth, right? Basically, which basically means edge is pointing away from the source. I will add source for a general language. Here it will be capital. Okay. Generally, this happens. Suppose if this is the graph, we will be going downwards, right? And this is another graph. And now, if you start traversing from this node, you will be able to reach this particular node because it is directed towards downwards or in the depth, you could say. And from here, you will be able to go in this particular node, but you won't be able to reach this node from the source node. You have to restart this particular thing and you have to come in this particular node by using a for loop iteration. Okay. Then you will check if it is visited or not, and if it is not, you will traverse from this particular node. Okay. But in this case, we have aimed that we will we will always start or we will keep the 0 as our source node and no other node will be a source node in this particular question, and we won't be using any for loop for iterating every node. Okay. Now what we will do? You can modify the graph and you can make it this way, bidirectional, fine. And here from here you could figure out that red color is the reversed edge, and yellow is the original. Fine. This you could figure out from here. Great. Okay. Now let's try traversing the graph. Okay. So from 0, can you come to 1 if you use the original node? You cannot, right? So what you will do? You will use the red color edge to come, which is the reversed edge which we use, right? So from 0, you came to 1. Okay. So which means that original edge was pointing towards 0, correct? Which is yellow color, right? So standing at 1. Now from 1, you tried coming to node 3 by using the original node, okay? But you were not able to use the original node or the yellow node. Not node, sorry, edge, okay? Yellow edge. So rather what you used the reverse edge and you came to 3, okay? So that means that visually we could see that 3 is pointing towards 1 and furthermore 1 is pointing towards 0 and basically they are all pointing towards the node capital node, right? So it is fine. Now from 3, you tried going towards 2, right? So you used the original node or the yellow node to go there, right? Till now you have used red colored node. So here this one and this one because the original node was pointing towards the capital city. So you were not able to go down. So therefore you use the reverse edge. Okay. Now from to go to 2 from 3, you use the original edge here, the yellow color edge, right? But does it means that it is pointing away? The original edge is pointing away now. Okay. Now, if original edge is pointing away from it, that means we have to reverse this particular edge, right? So if you could see, we have a red edge already present here, right? So what we could do, we could increase the count because to come from 3 to 2, we use the original edge, right? Which was given to us. But till now, we were using the red color edge, the reversed edge, right? Which subjectively means that the original edge which is given to you already is pointing towards the node 0, right? Which is the capital city. So you don't have to worry about anything of reversing. But from you were now, but you used the original edge from 3 to 2, from going to 2 using 3 from 3, you use the original edge, which means that that edge is pointing away from the capital city, correct? Therefore, if that node has that edge has to be reversed, right? So basically, therefore, so you used node 3 to reach node 2, you use the original yellow color node, which depicts that the original node is going away from the node 0, right? And we have already created a reversed edge there from 2 to 3, which says that fine. Therefore, that particular edge has to be reversed, right? So coming back to 3, you will be using the node, the edge red color of. So you will be using the reversed edge, which is of color red. Okay. So I hope you understood this point, what I'm trying to say here, right? The yellow edge is going away from the capital city, right? Therefore, we have created a reverse edge here so that we could go back to 3. Otherwise, we won't be able to go back, right? That's the thing. But yeah, so we increase the count in that case. We see that, okay, we went from the original edge, okay, and we didn't use the red color edge or the reverse edge to reach 2. Therefore, we increase the count. Fine. Okay. Now from 3, you were able to go to node 4 also, right? Here also you use the original edge, which is of green color, yellow color, right? This also says the same thing. Look, you are using an edge, an original edge, which is pointing away from the capital city, right? And we are not using the reverse edge. Therefore, it automatically means that this edge has to be reversed. Therefore, we increase the count to 2 here. Okay, so we're standing at 4. Now we go back. Okay, now from 0 you come to 6. Fine, you come here again, same story. You use the original edge, right? So it depicts that it's going away from the capital city, and we are not using the reverse edge, right? Therefore, this particular edge has to be reversed and the count will increase to 3. Okay. From 6, you came to 5. And what edge did you use here? You used the red color edge, which means that the original edge was pointing towards the 0, right? And since we use the red color edge, it automatically says that we don't have to reverse anything. Okay. Now from 5, you went to 7. right? But what you used, same story again, you use the yellow color edge, the original edge. It's pointing away from the capital city, therefore it has to be reversed. And since we have not used the red color edge, so the count will increase to 4. Okay. Now I will clear this up. Okay. Coming back. So this was the graph given to you, right? So if you can just visually look, you have to reverse this edge because it is pointing away. You have to reverse this edge because it is pointing away. You have to reverse this edge and this edge, right? So how many edges did you reverse? You reversed nearly 4 edges or equals or exactly 4 edges, right? Therefore, this is what I explained you, right? And but in code, you cannot write red and blue, right? So what you will do? A road that goes away from the current node, you could say that also, the original node, maybe may need to be reversed, right? A reverse edge added to the adjacency list help us to explore the graph, right? So what you do, if the original edge is there, you mark it as or you weight it as 1, and the reversed edge which you will add, you will mark it as 0. Okay. So this way we could identify which particular edge we are trying to use. Okay. I hope you understood this intuition and the visualization process. Now, how we can simulate this, right? So we can create a helper function which takes the node, parent, adjacency, and DFS and visited array, and it will be named as DFS. Simple. Okay. Why we are taking the parent? Just in case we have to check whether the parent is visited or not. Fine. That's all. Now, how we will create the adjacency list? Okay. Please pay attention to this. We are given A is connected to B. Okay. We have been given a directed graph. Now, what we will do? We will connect A to B and we will weight it as 1. Then we will connect opposite direction also this way and we will weight it as 0. So this is the reversed one which we created. This is the original one which was given to us. Fine. This becomes the bidirectional directed graph. Okay. This is what is explained here. And what we do, we travel on the edge and we check that if the edge which we used previously it was red. Okay. Please remember that. If the edge which we use is red or red means the reversed edge, right? Or and yellow means the original edge. Fine. And in this case, the yellow edge is 1, which is the original edge. Please keep that in mind. Here I have written already. And red means it is marked it as 0. Okay. So when we take the node or we go to the children of the particular node, we check that if the edge we used values to 1 or not, or weights 1 or not. If it weighs 1, that means the road is going away from the city 0. So we need to reverse it and we just increment the count. Okay. And we will be, of course, be able to go in more depth because we have already created it in a bidirectional form. Okay. But if the check is 0, the road is already directed towards city 0. Check 0 means the reversed edge you are using to go in depth because the original edge is pointing towards upwards, right? So you won't be able to go in the depth, right? I think this makes sense to you now. So we maintain a visited array, which is a common practice, and we start the DFS from node 0 and we do the traversal through the tree. Okay. And at the end, we just return the number of count of the reversed edges. Now, what we figured out? Every time we find a road that points away from the root, has to be reversed, okay? And otherwise we block the path, okay? The rest of the roads already help in reaching the city 0. So we focused only on edge going away, okay? This is the one which we mostly focused on, okay? Secondly, we used check as the keyword here, 0 and 1 to identify original. This one as original and this one as reversed. Fine. By modeling the graph, by modeling the problem of a graph as a tree and simulating a simple DFS from the capital, we efficiently identify only one necessary traversal and avoided redundant checks, right? So I hope you understood this intuition. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach and how we're going to solve it. Fine. Let's do by building the graph with direction information. Basically, we are going to create a graph which is pointing in the both ways, right? And we also check, we are given a list of directed routes, right? And we construct the adjacency list. How it is done, right? We do it like for in, or you could do it like for u comma v in graph given to us. Okay, You could do adjacency list as u dot append v comma 1. This is the original one, fine. This means that u is pointing towards v and adjacency of v dot append. This is the one which is created by us. Sorry, this will be u. Okay. This says that v is pointing towards u. Okay. So bidirectional. This way we can traverse a graph like an undirected tree. Fine. Now second step is that we initialize visited array and start DFS from the capital city. So we initialize a visited array of size n, of course, and we mark it 0, or you could mark it as with false also, your wish, of n size. Fine, we do this. And these all are done within the main function which will be given to us. And within that function, we will call the DFS also. And DFS will have no for loop because there is only one component. We are sure of it. So the current node will be 0, parent will be -1 if we pass parent, visitor will be passed, and the adjacency list also will be passed. Okay, and at the end we will return the count. Okay, this is what here. Now the step 3, perform DFS and count reversals. What we could do is that we could create a global function constructor, and we could initialize count variable there. Okay, self dot count. Okay, this way. This is the constructor in Python. Okay, so we can access the count variable globally. When we mark the current city as visited when we come within the DFS function, it goes like visited of the node which is passed, mark it as true because it is visited. Okay, then what we do? We go for a for loop, or basically to the child of the particular node. We could use the variables child comma node, not node actually, direction. Basically zero direction. This is direction. This means 0 or 1. Okay, and if it is the child is not visited, okay, the child is not visited, we check if the direction is equals to 1 or not. If it is equals to 1, that means we have used the original path to go down. Okay, therefore we increase the count in that case. Okay, and we call the DFS again. Fine, we pass the child here, parent as the node, and that's all. Fine, this is what it is written here. And this process ensures that we visit all the cities. For each road, we check if it is facing the wrong way. If it is, we add our reversal count. Fine. Now in step 4, we return the final count. And after every count is done in the particular function, we at the end, when the DFS call is completely done, we just return the count in the main function which is given to us. Right? That's all. So I hope you understood the approach explanation. It's pretty simple and straightforward, nothing much complex about it. We just have to crack the intuition and in how we could resolve the question in one traversal itself. That was the main thing to understand. Now the code is the exact copy of the approach we discussed. Let's understand it line by line. So we declared the count variable globally here. And this is the DFS function. We mark the particular node as visited as true. This is not required. Okay. Then we go for the, if we clear it properly. Okay. So we mark this visited as true, node as true. Then we check if it is visited or not, or if it is the reverse original path we took or not. If we took, we increment the count, and this is not required. Okay, because we already have marked as true. Then we pass this child here, the parent node and the adjacency list and the visited list. Here, this is the adjacency list which we create. This is the original direction with value 1, and this is the reverse direction with value 0. This is the visited array, and this is the DFS call, and we return the count. Now, the total time complexity for this becomes O of n. Okay, but in general graph problems, what happens is that time complexity comes out to be n plus e, right? Now let me explain you why O of n is here. N represents the nodes, correct? This represents edges. E represents edges, right? But in this specific problems, we have n nodes and n minus 1 edges because it is a tree-like structure. Okay. So what happens is that if you do n plus e, it's n plus n minus 1, and it becomes 2n minus 1, right? Which basically simplifies to O of n. We go O of n, right? That's why the time complexity is O of n. But in general, you could say the time complexity is n plus e, but it will, but saying O of n will be much more clearer and much more logical for this particular problem. And same with the time complexity. N takes for this particular visited array, and again adjacency list is created with m plus e. And since again the nodes are n and edges are n minus 1, we do the same calculation and we get space complexity as of O of n itself, right? Therefore, the time and space complexity are O of n for both for this problem. So I hope you understood the code explanation and along with time and space complexity. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the diagram of the example. Okay, let me draw the graph for this particular problem first. Okay, so I have drawn the graph here and we also have the code here for better understanding. Now, let's do the diagram. So, adjacency list denoted and we have created the original directions. Okay, now let's create a reverse directions also. It points toward this, 0 will point toward 4 and towards 1, towards 0 and towards 1, and this towards 2. Okay, and please keep in mind that yellow stands for 0 here. Okay, and red stands for 1 here. Okay, basically 1 means original here and yellow means reverse here. Fine. I hope please keep that in mind. Okay, now let's do the traversal. You create a visited array also. Let me create that also. 0, 1, 2, 3, 4, 5. So I have created a visited array here. This is the visited array. Okay, this is the count and let's do. So it starts from the node 0, the capital city. Now we thought of going to its children nodes, right? So what happens? DFS call comes here. Please ignore this particular visited. So you mark this particular node 0 as visited. Then you check its children. So you thought of going to node 1 first, okay? And you check it is not visited. And to come to 1, you used the red color edge, right? Red color edge value is 1. You saw here check equals to 1, right? So you increase the count to 1 because you used the original node because red is the original node, right? Therefore, you use the original node which is going away from the capital city. Therefore, the count incremented to 1. Okay. Now from 1, now one from 1 we will call the DFS. Now, so you mark the 1 visited again here. Then you check for its children nodes. So there is 3. Okay. And it is not visited. To come to then you came to 3. To come to 3, you used which node? Which edge? You used the red colored edge whose value is 1, which is the original edge. Therefore, this condition becomes true if check equals to 1. So you increase the count to 2. Okay, done. So you call the DFS call again with 3. Then you mark 3 as visited. Again, you check the children nodes of 3 here. Since 1 is already visited, so you go to 2. And to come to 2, you use the yellow color edge, right? Because 1 is pointing towards a different direction. So yellow is 0. Okay. Therefore, the check equals to 1 condition becomes false and then nothing happens. Okay. So from 2, you try to call the DFS, but there are no more nodes and 3 is already visited. So you roll back to 0 again. Okay. Now from 0, you go to node 4. Okay. And you mark the node 4. Okay. Wait. So it is standing at node 4. Okay. Now, which edge did you use? To use edge yellow, which is 0. So the check condition falsifies and nothing happens. So you pass node 4 in the DFS call, and now the DFS call is going to call from node 4. So you mark 4 as visited. Then you check for the children for the node 4. Since 0 is already visited, so you go for the node 5. So you came here and you used which edge? You use the red color edge, which is the original edge with value 1. So you check, okay, check value equals to 1, which is true. So you increase the count. Okay. Then again, you call the DFS function from node 5 to come here again, the DFS visited node, and you mark this 5 as true. Now, since there are no more children to the 5 and 4 is already visited, you roll back to the node 0 and the complete DFS call is done. Okay. So after that, this particular call is done, you return the self.count. The count value is 3. So output for this particular problem is 3. Okay. So this is the complete diagram. It's just pretty easy and pretty straightforward. So if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition. and also the DFS concept if you don't have any idea about it. Then the approach and the code. After that, do a trial by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's go to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Okay. So let's start by writing the reading the adjacency list. Okay. For in range n. Since n is already given to us, we will create the adjacency list now. Adjacency of u dot append v comma 1. This is the original edge or original path. Adjacency of v dot append u comma 0. This is the reverse edge which we added. After that, we created a visited node, sorry, list with value false of n size. Then we call the DFS function. Start with 0. I guess we don't have to pass the parent here, so we could skip that. We could pass the adjacency list and visited array, and we will return the self dot count. Okay. Now let me declare the count variable globally. Now let's declare the DFS function here. Self the node adjacency list and the visited array. We'll mark the visited node as true first. Then we'll go for its child and the direction, which is basically 0, 1 or 0 and 1. Adjacency of node. We'll check if not visited. Child is not visited. Then we check if direction equals to 1. We do self dot increment the count, and the DFS function will be called whether the direction is 1 or 0 because we have to go in the depth, right? Therefore, it is outside of the if condition of the direction one. So we pass the child node here, adjacency list, and the visited array or list. So let's try submitting the problem for the sample test cases. Sample test cases got accepted. Now finally submit the solution. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.